going on to 1.1 here, starting chapter 1. All right, you don't need to write everything down. Probably maybe good things to write down is definitions if you need to be, formulas, obviously, right? But the rest of it will be really just writing down or doing practice problems here. The lecture notes, right? Notice they're just practice problems here. So I'll do a little bit of sort of copies from the textbook here. Those are ones that sort of need to be addressed. Anything there's a like a definition of things I'll mention, but then really you want to jump to the practice problems here. All right, the other thing I want to mention is since you have the lecture notes in front of you, the good thing one thing I did think worked out well last summer, and I taught Math 61, is I just allow them just a couple minutes by the time I start a class just to do as many problems as they can on those lecture notes. So then when you've done that, then you go back to it, and then you're sort of just putting in the missing pieces. Does that make sense? You really are understanding, like, wow, I didn't get number 5. Now I got number 5. Right, so kind of be mindful of that. Maybe Thursday before class or right at the beginning of class, if you walk in a little bit early, just start those lecture notes. Start doing the rest of them. Because then when you start class, then you're just going to be filling in the stuff you don't know. All right, with that, though, let's go for it here. So we use variables like a and b, x and y. Those represent those represent numbers. We call those variables here. The other thing is right here, notice we use notation sometimes. Like if you see this right here, notice that there's a 10 in a parenthesis. We understand that right between the 10 and that parenthesis, there's a multiplication symbol, right? So there's a few symbols that we sort of assume, okay? And if you like somehow you didn't get it, please ask me. We'll go for it, okay? Easy enough to do so. All right, I think you guys know this already here, but equal sign, and if you want to write not equal to, all we do is we put a slash right through that equal sign right there. And then we have the inequalities. Inequalities, there's a less than b, a greater than b, a greater than or equal to b, and then a is less than or equal to b. Again, all these are in your textbook, so if you want to turn to them or bring your textbook to class, that's cool too. All right, there's one thing there. So how we compare numbers to each other. That's kind of really it. It's comparison symbols. They are either equal to or not equal to, or they're compared to each other by an inequality fashion. All right, then we have the operations, which I think you guys know. Plus sign for addition, minus sign for subtraction, and then multiplication gets crazy. So before algebra, remember we used to use that big O X for multiplication? I don't know why they do that, because we should just get rid of it altogether. It should be just a dot. That little dot right there is multiplication. 2 parentheses next to each other is multiplication, or 1 parenthesis on the side of a variable or a number, or variables by themselves close together. That all means multiplication. Division has 4 different symbols. You can write it as this right here, just the division symbol. You can write like a slash. You can write it as a quotient, one number over another number. Or you could use the division symbol of long division. So 4 different ways we interact. It just all means divide, no matter how you write it. All right. And then parentheses, grouping symbol, something you'll see here. So parentheses, bless you, and brackets. We use these guys, we use them 2 different ways. First is something called order of operations, right? I think you guys remember those. Also, we're going to use these in terms of something called intervals. So there's 2 different senses we use it. We'll get there as well. Okay, occasionally we use braces as well for grouping symbols. All right, but anyways, almost ready for our first problem here. So the whole concept of exponent. Exponent, if you have 2 to the 3rd power, that little number on top just means how many times that number is being multiplied together times itself, right? 2 to the 3rd is 2 times 2 times 2, which really is just 8. So this we have phrasing from English into mathematics. Now this one's something new, not in your textbook here. What I'll do before the class is done, let me print this out for you and you can take it so you don't have to take the time right now to sort of go through it. So if you say sum plus increased by more than added to, that all means addition. The only funny thing is if you say 5 more than 7, you're saying the 7's already been there, right? And then you're going to add 5 more to it. So there's kind of like a backwards way to writing those. Or you can say 5 added to 7. Well, that actually means 7 plus 5, right? Less than or subtracted from work exactly the same way. And in English, we sort of say it backwards in the operation itself. So be mindful of that. That comes up in the class a few times here. Anyways, product times over twice. That all means a multiplication. And again, I'll print this out for you before we finish today. Occasionally, what I'll do is I'll actually put up the example from the textbook itself. Sometimes the example in the textbook is way different from the practice problem or what you have on your sheet of paper. Sometimes I want you to introduce it before you start on something more difficult. So I'll sort of do that from time to time. But anyways, I think we're good to go here. So expand and multiply this. So 7 squared really just means 7 times itself twice. So 7 times 7, I'm pretty sure that's a 49, is that right? Cool, all right, how about 2 to the 4th power? And 5 to the 3rd power, all yours to do that, if you're not done already. All right, what's the other thing is? The other thing is, since I'm recording as well, I'll ask, anybody not ready to go on to the next slide? Tell me before I go to the next slide, because I can't go backwards. Once I go to the next slide, I have to be on the next slide. Cool? So if you're not ready, raise your hand real quick here, and I'll wait a little bit longer on that slide. So 2 times 2 times 2 times 2, that's what it really means. There's 4 2's multiplied together. At this point, it doesn't really matter which way you multiply. You can go from left to right normally. So 2 times 2 is 4, 4 times 2 is 8, and I heard 16 already. That is true. 5 to the 3rd power, which means 3 5's multiplied together. So 5 times 5 is 25, and then 5 again. How about a 125? All right, what's the other thing I want to mention is chapter 1. Chapter 1 is really not algebra. It's more like just a review chapter, okay? So if you are saying, Mr. H, chapter 1 is the most boringest thing in my life, I know it already. That's a very good thing. That means you're ready for this class. We good? Or you can say, man, chapter 1, for the most part, it was really, really easy. That's good too, okay? If you're really having trouble in chapter 1, that's not a good thing, because this is really just, it is pre-algebra. We're going to review pre-algebra in one single chapter. All right. Thanks, sir. Raise your hand if you have not signed the sign-in sheet. I think I already did. Okay, real quick here. So with exponents, sometimes what we do is we have like sort of special language here. If you're taking 5 to the 2nd power, what we do is we just say, call it 5 squared. And the reason for it is because it makes a square area. You're just thinking 5 times 5, it makes that square area. All right, if you're taking anything to the 3rd power, instead of saying 5 to the 3rd power, sometimes I'll say 5 cubed. The reason why it's cubed is because a length and a width and a height will actually make a cube. And so that would be 125, but it would be cubed. Also, whenever we square something, let's say it was 5 inches, we square it and it becomes inches squared as well. So the units are squared as well. If you say 5 cubed, again, if it was feet cubed, then you have feet cubed, right? Then you have yourself a volume indicator. Okay, cool. All right, and one little extra thing here, just like in English, I'm going to say commas matter even in mathematics. So if you say Paul said John is tall, just depending on the punctuation, where things are at, where's the period, where's the parenthesis, where's that, it can mean 2 different things, right? So in English we say Paul said John is tall. Who's doing the talking? Right here. All right, John, right? Isn't John talking about Paul? For number 2, who's doing the talking? Paul. Paul now is talking about John. So same thing in algebra. I'll say, no, you need a parenthesis here. Like, why can't I use a bracket? Because you can't use a bracket. You need a parenthesis. And so we'll have that discussion. Good. Okay. with that said, let's go to order of operations here. Order of operations. In fact, I like to, this is my version of the order of operations. If you want to write it down, here it is. All right, I usually find just a handful of students that have learned order of operations wrong, and we'll talk about it here. So I have P for parentheses, E for exponents, and then the M and the D, they actually should belong on the same line. The reason why they belong on the same line is because you do them at the same time. So if you look through it, anytime you see multiplication or division, as you're looking at it from left to right, you're going to do that operation. Good? Addition, subtraction, the same thing. Even though subtraction may come earlier, or if it does, then you got to do the subtraction first. Cool. And I usually find like 2 or 3 students, usually in the Math 61 class, like, whoa, hold on, I didn't learn it that way. So if you did learn it the correct way, that's cool. Let me give an example to make sure. And we'll go from there. All right, I think we're ready to go on. Let's try this one here first. So simplify this, 7 plus 3 times 4. So think about it here, which one would go? Or how would you do this problem here? And we'll go from there. So order operations, there's no parentheses, that's great. No exponents, even better. Any multiplication or division? Yeah, just between the 3 and the 4, is that right? So that has to come first. The 7 sort of stays on the outside still. But I got myself 7 plus 12 now. And eventually, how about a 19? Right? All right, here's where we test whether you learned it correctly or not correctly here. So I got 15 divided by 3 times 2. What should we do first? Yeah, remember, multiplication and division come at the same time, right? Whatever you see first coming from left to right. So as we do this here, we go 15. Oh, 15 divided by 3, that's going to come first. So 15 divided by 3 is a 5. And then 5 times 2 is 10. Are we good there? Out of curiosity here, and that's cool too. I say, Mr. H, I didn't learn it that way. I learned it, they just go multiplication first. 1, 2, see? 2 honest people in the whole class. All right. So Kara, that's the only one, and I think it's because in elementary school, when the teachers write it, I think what they do is they sort of write it down like this, don't they? They go like this, because they're trying to get the acronym of "Please excuse my dear Aunt Sally," right? But they forget to mention that these 2 and these 2 actually are together, right? They're in the same time, left to right. Good. All right, C, all yours here. Go for it. Give you a minute or so, try it yourself. All right, so this is what I got for C here. So I'm going to work with the inside parentheses the most. Everything else stays the same except for inside this extra little tiny parentheses. We start with the innermost grouping symbols. So we start with this here. Let's see, 5 plus 2 times 3. Of course, 2 times 3 is going to go first. So everything else remains exactly the same, except for 2 times 3 is 6 now. Good there. So you go from the inside out as you go. Good. Then inside the parenthesis itself, 6 plus 5 is 11. And then I'm done. There's nothing else to do inside that parenthesis, right? I did multiplication, I did addition. So now I go on to the bracket. And I'm going to do the bracket. Notice, forget the 3 on the outside for now. It's just going to be all about what's inside the bracket. Any parentheses inside the bracket to deal with? Nothing that needs to be simplified. Any exponents? Nope. Any multiplication or division? Yeah, it's the 2 times 11 over here, right? That becomes a 22. 22 plus 4, that's a 26. So notice now I've done everything inside that bracket because it's called an inner grouping symbol. Now I finally take a look at everything on the outside. So I say to myself, everything starts all over. Any exponents you see? No. Any multiplication or division? Yeah, 3 times 26. Cool, 3 times 26, multiplying that out gets you 78. We good? So we go from inside out always with grouping symbols here. Two more for you. All yours. Go for it. All right, I'm going to try it as well here. Let's see. Look at this here. No parentheses, no exponents. That's cool. Any multiplication or division went from left to right. Yes, 10 divided by 2, right? Is this little portion right here that I get to do? So that becomes 5. Good there. Then I start looking at it again. Any multiplication to division from left to right again. Okay, there's that 3 times 4. It becomes a 12. Good. All right, from here on out, then it's going to go from left to right again. 7 plus 5 is going to be 12. 12 plus 12 is 24. Good. All right, this one, let's go for it. A little bit more difficult. No parentheses. That's cool. Exponents, yes. Now notice the exponents are separate from each other, right? So you could do all the exponents all at once. When we get to chapter 7, I believe, we're going to really deal with exponents and how that works. But for now, they're all separate. Let's just deal with each of them here. So 5 squared, whatever that's going to be. 4 to the 3rd power, so 4 times 4 times 4. 64, perfect, cool. Divide by 2 here, I'll keep it like that. And then minus 3 squared. 9 is good, okay, cool. Okay, from here, now we go. Let's see, x1's done. Any multiplication or division from left to right? Just the 64 divided by 2, right? So boom, that's 32. Cool, and then I go from left to right. Any addition or subtraction? 25 plus 32. 57, subtract 9 would make a 48. Are we good? All right, out of curiosity, how many got all 5 correct? Sweet, okay, cool. All right, the other part in mathematics is this whole concept of reading tables and graphs and charts and stuff. That happens quite a bit in whatever profession you're going to be in, because then you got to be able to read some charts here. So just a quick intro from the textbook here. This is example 3, and then you guys get to do practice problem number 3. But you have a brewed coffee, you got instant coffee, tea, cacao? No. Anybody say it? I don't know. Cocoa is good enough. Okay, decaf coffee. This is the caffeine content. And so let's see, referring to table, suppose you have 3 cups of brewed coffee, 1 cup of tea, and 2 cups of decaf in one day. How much caffeine did you consume? Way too much caffeine. So notice the 3 is going to be your multiplier, right? It's 3 times. How much is each one? And last semester I thought this was silly. Like, who drinks coffee and then drinks decaf coffee? How many drink coffee and also decaf coffee in the same day? Cool, okay, see? No one's weird here, all right. Well, last semester I had like 4 people raise their hands. Mr. H, we do. Like, why? Well, in the morning you get a whole bunch of caffeine to start your day, but then you still want that coffee flavor at night, but you don't want to be staying awake. So then like after dinner, you get like decaf coffee. Like, okay, that's fine. Not as weird as I thought. So here's ours. Referring to table and the chart, suppose you had 2 cups of brewed coffee in the morning, 3 cups of tea at work, and then 1 cup of decaf in a single day. Can you tell me how much caffeine did you have in that one day? right, so 2 cups of brewed coffee. Well, each brewed coffee is 100 milligrams of caffeine, so it's gonna be 2 times 100. Then we have, let's see, 3 cups of tea, and tea is 50 milligrams of caffeine each. So how about 3 times 50? And then we have ourselves the last one, which is 1 cup of decaf coffee. You really don't need to multiply by 1 anyways. But how about 200 plus 150 plus 4 more, or 354? And of course, whenever you do word problems, you got to give your unit value. What are we talking about? 354 pounds, elephants, desks. So it's good. Milligrams of coffee, or milligrams of caffeine. Sorry, not coffee. It's caffeine. Milligrams of caffeine. Good. Okay, are we good there? Again, just reading charts. We sat all the faculty and all the, before the semester starts, we actually go to school on Wednesday. So Wednesday, Thursday, and Friday. We sit in meetings all day long. It's super fun. But every single one of those presenters presented graphs of some sorts, whether it's enrollment for the school, whether it's, whatever. So kind of funny. The math instructors, we sort of all sit in the same table. We try to figure out if something's wrong with the data. It's kind of fun. Usually there's something wrong with the data.
I have a question. Are you going to want us to show a problem like that, or can you do like 2 memory?
Got it. Good question here. The question is, how much work do I need to see, especially on the paper and pencil homework? I figure this: if I can't do it in my head, you certainly shouldn't be able to do it in your head, or you don't belong in this class. Okay? So my rule of thumb is, if it's reasonable for me to get to one point and logically follow your steps in the homework, that's cool. If you go from here and you're ready 4 steps later, like, no, that's not possible for a Math 61 student. Cool? So somewhat lenient, but kind of just be mindful. Good question. All right. The other part is just looking at patterns here. And so we can just sort of quickly look at this pattern here. So can you find the next number in the sequence here? So we go from 3 to 8 to 13 to 18. What are we doing, anybody? Adding 5 each time. So this actually is called an arithmetic sequence because there's some kind of addition that we're using. We good? This is an example from the textbook. We'll have our own practice problem just a bit here. How about this? What am I doing if I go from 2 to 10 to 50 to 250? Multiplying by 5 now. This is called a geometric sequence because it's a multiplication sequence on our hands. Good? So you can add, you can multiply. How about 2 to 4, then 4 to 7, 7 to 11? Oh, cool. Okay, so this is a weird one. So notice from 2 to 4, you added 2, right? But from 4 to 7, you add 3. Then you add 4 to get to 11, right? The next one you would add 5 and you get 16. We good? So the number itself is getting higher as well as you're adding. Okay, we've got some sequences for you guys. Go for it. Can you just give me the next number in the sequence? That's it. Just go for it. All right, I'm going to start it as well here, if you guys have it here. So 5 to 9, 9 to 13, 13, 17, what are we doing? Adding 4 each time, perfect. So the next number would be 21. Good by me. Yep. This one, 3 goes to 12, then to 48, then to 192. Multiplying by 4, perfect. And then 192 times 4. Awesome, 768, perfect. Okay, 3 to 6, then to 10, then to 15. Perfect. Yep, the numbers increase by 1, right? But 3 goes 3 plus 3, then plus 4, plus 5, plus 6, and eventually 21 as well. Okay, and again, these are just basic ones. We actually will go in depth on each one of these here a little bit later on, cool, as we progress through chapter 1. The fun, unusual one is this one right here. So see if you guys can guess this one here. All right, and the fun, this one right here. It's called the Fibonacci sequence. And so you guys tell me here, if you go from 1 to 1, then you go to 2, then you go to 3, then you go to 5, then you go to 8. What in the world is happening here? Okay, talk to me here. Give me an example. It's right there. There you go. Mr. H, it's there. What's the matter? Let's talk about. So 1 plus 1 is 2, and then you take this one. 1 plus 2 is 3, and then 2 plus 3 is 5, and 3 plus 5 is 8. So you're taking the previous 2 numbers to get to the next number, and then you take those previous 2 numbers. This guy's name, this is his math name. It's called Fibonacci. He got a nickname in mathematics. He was that good. But his real name is Leonardo da Pisa. You guys remember the Leaning Tower of Pisa? Back in those days, we didn't use last names. We just used where you're from. Right? So Leonardo da Pisa means Leonardo from the city of Pisa. What he did is he actually gave us the number systems that we use. So back before his time, this is 1550s, 1560s, we calculated using Roman numerals. Could you imagine multiplying by Roman numerals? Leonardo da Pisa, he was born in a somewhat rich family, so he got to tour the world. Kind of cool for a while. And so being interested in mathematics, he was looking at, I think somewhere in India. He was traveling through India. He was traveling through the Arabic states there. And he knows, wow, these guys don't use Roman numerals. What are they using? And so they were using these numbers right here. It's a base 10 system. It's like, that is fascinating. So he brought it back to Europe. And ever then, we started doing the same. All right. Yeah, there's that one more right there. So number 5. So use the first 10 Fibonacci numbers. So you're going to write them out first. And then can you give me 2 more afterwards? So the first 2 are 1 and 1, right? Then you add those 2 to get a 2. Then you add 1 plus 2 is a 3. And keep on going. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. 8 plus 13 is 21. How many? That's 1, 2, 3, 4, 5, 6, 7. I gave you 8. So you got to find 2 more to get you 10. Then you got to find 2 more after that. Right, if you haven't done so already here, let's go for it here. So 13 plus 21 is 34, sorry. 21 plus 55, heard, yep, Adding from there gets you an 89. And eventually adding to the end, how about 144? And then again, 144 is also special. Something about 12 times 12. It is a perfect square of 12. And the first perfect square in the Fibonacci sequence. And then in math, this is where the fun part begins. So the question is, is there another perfect square within the Fibonacci sequence? And then there's math theory. There you go. Okay, I want to show you a little video of this Fibonacci sequence. And then this is where I find math just awesome, because math has so many ramifications to so many things. It sort of just builds and moves on everywhere, okay? Let me see if the volume is on. Yeah, maybe too loud here. Let me bring it down. Okay, so this is the Fibonacci sequence. So this artist in conjunction with a mathematician they just said, hey, let's look at Fibonacci sequence. Let's see where it takes us. That's kind of. Should recognize that's the Fibonacci sequence there. Stop it right there real quick here. But this whole concept of math just sort of extending out to different pieces. Anybody, anything this reminds you of right here? Honeycomb, there you go. So then again, you can keep on going and going. We good? Just kind of, so just real quick, you rewind here. Start off with the Fibonacci sequence. And the Fibonacci sequence, as you put the blocks together, one and one, they form perfectly sort of like a side of a square, right? If this is a 1 unit here, all of a sudden, then there'll be a square that's size 3, which actually will fit right on the side here. We good? And then if you put the 3 here together, that's 3, 4, 5. Now you got this square, which is another piece of the side of another square using a Fibonacci sequence. We good? So this sort of builds out. Then the question is, what happens if you just touch the corners right here? Touch the corners and keep on extending it out, go further and further, and if you look at it, it just becomes a spiral, and that spiral it becomes what we call a mollusk. So there's those individual places where it touched the side of that square. So then right here, this is a different number. This is called the number phi. Again, shows up in mathematics quite a bit. And we call it one of the most surprising numbers. All of a sudden, like, whoa, hey, that's phi right there. Wow, as we look at stuff. So if you take the ratio of that and you start doing circles and pinpoint. Each time it hits 137.5 degrees, bless you, eventually you have, let's go to here, you have modeled the position of seeds in a sunflower seed. And so once you do that, and again, connection to the dragonfly, you take these seeds here at different locations, you build a hexagon to each one of those, and then you take the sides of them, and what happens is it turns into the model that you can use for a wing of a dragonfly. And so notice these are just more different shapes, but you could take random, in a sense, positions of a sunflowers and sunflower seeds in a sunflower. So I thought it's kind of cool how math sort of just goes into all these different areas and just kind of keeps on flowing. Anyways, let's go from there here. Let's see, about 10 minutes left, but I think we can push this out real quickly here. Let's get through 1.2 at least today. So now we're talking about real numbers. What real numbers are, anything that fits on a number line. If you could put it on a number line, you got yourself a real number. So number lines also have positive and negative numbers. The question is, hey, when do we ever use positive and negative numbers? One example, which the book addresses, is temperature, right? Don't we have negative temperature? Absolutely. We have positive temperature. Another one is something called debt, which none of you guys know, right? You owe some money to somebody. So number line is made. They have coordinates here, so it looks like this. So now can you place a negative 2.5? And again, because we have only a certain amount left, I'm going to kind of quickly run through these here. So negative 2.5, if you start off with 0, you're going to go negative 1, negative 2, and a little bit more. So it should be about right there. We're good. And then because you are listing everything on one number line, whoa. All right, some weird stuff happened here. I don't know. Okay. So from here, negative 3/4, again, it's not quite negative 1 because we always go away from 0, negative 3/4, which means it's 3/4 of the way to negative 1. Okay. All right, positive 1/4, starting off at 0, going off to the right this time, and just a little bit away, a quarter of the way to 1, but not right there. How about 2 3/4? That means we have 2 whole pieces. So 1, 2, and then 3/4 of another piece. So 3/4 of the way to 3 from the 2. So how about 2 3/4? All right, and 3.5 should be easy one here. That's a decimal. So 1, 2, 3.5, or 3.5 would be about right there. So there's my 3.5. All right, you can write it either above or below the line, whichever is fine with that. Okay, good there. Then we have some, whenever you have a fraction, you can have different numbers, but they really convey the same idea. What is the idea convey is the distance away from 0. So if you say 0 to 1/3, this is a distance of 1/3 here. If you break this number line up into 6 pieces, this will be 1/6, this will be 2/6, but notice real quick here, 1/3 is the same thing as 2/6. They are in the same position away from 0. We good? So we say, you know what, 1/3 then is the exact same value as 2/6. We good? And so let's do a little bit of work there. And of course, you can extend it down. So 1/3 is the same thing as 2/6, which is also the same thing as 4/12, right? We can have a whole bunch of equivalent fractions here. All right, so with the way the book does it, it wants you to figure out, can you write 4/5 as an equivalent fraction and a denominator of 20? So the denominator has to be 20. All right, well, how do we do that? Well, let's list down 4/5 equal to, now we have to make a fraction, so the denominator is 20. All right, so what's so special about equivalent fractions is that whatever multiplier you have on the bottom, you have the same exact multiplier on top. So we think to ourselves, what multiplies 5 to give you 20? That's going to be a multiplier of 4, is that right? Therefore, you have to have this exact same multiplier on top, and that is going to be a multiplier of 4. So 4/5 is the exact same thing as 16/20. Those mean the exact same thing. All right, we'll run through the rest of this kind of quickly here. Next thing is the whole concept of absolute value. We use absolute value, we'll use it in this chapter here, but real quick here, I took this from a different textbook here. If you say absolute value of 5, why is absolute value of 5? Because it's the distance away from 0. So 5 over here, the distance from 5 to 0 is 5. So -3, if we position -3, what's the distance from -3 to 0? 3. So notice the positive numbers stay positive. And if you have a negative inside, that just changes into a positive. But absolute value numbers will always be positive numbers. Okay, good there? That's why we dropped the minus sign there. All right, absolute value of 4. Better be 4, right? Absolute value of -4. Awesome. Absolute value of -5/6. 5/6. You guys are too cool. Okay. All right, so now let's throw a little bit of maybe like statements or expressions and absolute value here. So absolute value of 9 minus 4. Yeah, got to do the stuff inside here first. 9 minus 4 is 5. And then the absolute value of 5 is a 5. Good? So we've got to do the stuff inside the absolute value first, and then see what happens at the end here. So in this case, stuff inside here, no parentheses. I do see exponents though, so 2 squared and 4 squared. So how about that? That 2 squared becomes a 4. 4 squared becomes 16. Any multiplication or division? Yeah, 5 times 4 is 20. Also can do 3 times 16 is 48. Adding those up gets you 68, and the absolute value of 68 is just 68. All right, and C, notice the absolute value starts and stops here. So this one has multiple absolute values in it here. So 15 minus 5 is 10. 11 minus 4 is 7. Then I'm going to take the absolute value of each of those. So it's 10 minus 7, and then eventually it becomes a 3. All right, the other vocabulary term that we got to learn is something called opposite. And opposite just means you go to the exact opposite side of the number line. So if you say, what's the opposite of 4? You're going to go all the way to -4. What's the opposite of -4? +4. So you just sort of flip across the number line. What is really happening is just change the sign. Now for these, don't put an equal sign next to it. Don't do that. Just kind of write off to the side, just write the opposite. So in this case, you say for A, it's -7. Good? Just change the sign. B, +9. C, -2/5. And D, now a +4/7. Before we get to D though, I want to stop you just a little bit at C, just to sort of show you something here. Whenever you have a fraction, and you have a negative here, the negative could either go on top, if you put a slash as your fraction. The negative could go in front of a quotient, or the negative could go on top of a quotient. All these are really the exact same thing. There's no changes there. All right, and D, to finish it off, +4.7. Okay, the bell rang, that means I got 2.5 minutes left. It's kind of like my 2-minute warning. Let's go to multiplying fractions here and then doing reciprocals here. So multiplying fractions, how do we do that? Is we just multiply the tops together and multiply the bottoms together. So if A over B times C over D, it's just going to be AC over BD. So we multiply straight across, and then we'll get to more complicated ones later on, but for now, just doing the easy ones. So for us, here we go, is 4/5 times 2/3. Multiplying the 4 and the 2 together, multiplying the 5 and 3 together, done. And of course, we're going to be cross-canceling later on and all the good stuff here, but just to get us started here. So how about 7? 7, you have an 8 in front. 8 is not a fraction. So what we do is we make 8 into a fraction. How do we make 8 into a fraction? Put a 1 underneath it. Yep, so no, the 8 goes with the 2, 1 goes with the 5, and multiplying it out, how about 16/5? All right, and the question comes up, Mr. H, do I change this to a mixed number or keep it improper? Answer, almost always keep it improper, unless it says to change it to mixed number. In algebra, it's much easier to work with a improper fraction because you can plug that one in real quick as opposed to changing it to a mixed number and then putting it into an equation. Not cool. Number 8, 3/7 squared really just means 3 7s times another 3 7s. Multiplying the tops together anyways, 3 times 3 is 9, 7 times 7, 49. All right, there's that vocabulary to learn, or process to learn with fractions here. All right, another one's something called reciprocal. Again, we're just kind of getting vocabulary here from pre-algebra. Reciprocal just means you're changing places between numerators and denominators. So give the reciprocal of each number, reciprocal of 8. 1/8, yeah. Technically 8, we just said 8/1, right? So if we switch numerator and denominator, it would be 1/8. How about reciprocal of 3? All right, how about if something is already a fraction, 1/4? Perfect, cool. You can write it as 4/1, but really you really don't need the 1 underneath there unless you're using it for something. We just write 4. All right, reciprocal of 4/5. 5/4, perfect, cool. All right, and one more problem to go, and we're out of here. One little mention here real quick here. With reciprocals, we never change the sign. Notice all these guys are positives, and it stays positive. If you're taking a reciprocal of, let's say, -4, what we do is we leave the negative on top or in front of the fraction itself. Good. So the negative stays on top or in front. And then we have these formulas here. Formulas of a square. And again, anybody know what page number this is? Let's see. Anybody that has a book here? So maybe a good one to sort of go to. I don't know. So I'll leave it there here. So here's our 19 says so. All right. Looking at this here, we're going to use these formulas here. So perimeter of a square, since all the sides are the same, it's just 4 times the side. Area is one of the sides squared. Perimeter formula for rectangle is 2L plus 2W, because that's the fence around. Think perimeter, think sort of like the fence around. Area is length and width. Perimeter for a triangle, well, if it's the fence around it, it's just going to be A plus B plus C. It's all the way around like this. And then the area would be half the base times the height, or half the width, the one that's perpendicular. Again, if you need them, you can get them real quickly here. So real quick here for these guys, not so much as just getting the answer, is plugging into a formula and then plugging into the formula to get the answer. Good. So it kind of looks like this here. So we want a perimeter of an area. You get the formula from the previous slide. You say, okay, it's 4 times S. You plug in the S as it should be, multiply, and then put your unit values. We good? So in algebra, you're more working with just using the formula to get where you need to get to. Area is S squared, or one of the sides being squared. Plug in the 3, square root of 3 gets you a 9. Now for area, the units also have to be squared, right? So you're looking at how many square feet fit into that. There's going to be 9 that's going to fit into that. All right, and then let's go from here. Formula, plugging into the formula, simplifying as much as you can. There's 24 inches. Let me write down the rest of it. However long it takes to write it, go for it here. Okay, area is length times width. This would be 7 times 5, or 35 inches squared. Perimeter for a triangle is all the sides added together, which eventually gets you 105 meters. And then the area is 1/2 times the base times the height, plugging that in. At this point, what I would say, especially with that 1/2 in front, I would just say half of 40 is 20. And then 20 times 27 would be 540, and again, meters squared, because area is always in terms of square units. Sorry, left the most complicated one all the way to the end here.